we were talking about what makes the gradient flow create this so-called problem of vanishing gradients. We had a very simple analysis using the chain rule and backpropagation, and we have seen that since in backpropagation through time, you're updating the weights over themselves. You're using this rule, and according to the length of the sequence, S or N, backpropagate, truncated K, whatever, you come up with this formula. The gradient value calculated for different activations and biases, because the weights are the same, but as the activations change, these will be different, and the weights updated will be multiplied with each other. So either this guy or this part is very prone to reach zero, we have analyzed. Not necessarily zero. Nobody can say that they are definitely zero. However, when you're doing something tens of hundreds of thousands of times, just like we do in backpropagation, because we will have large scale data, statistically, we can say that this guy will most of the time reach to zero, and this will affect our training most of the time. That's it. That was just what we said. And actually, this analysis, the simple analysis, leads us to the fact that it is very difficult to train recurrent neural networks. And actually, Jeffrey Hinton has a very famous speech on YouTube, the difficulty of training recurrent neural networks. I recommend you just watch it. I think I put it on the additional reading slides and part. If I didn't find it, he tries to explain this. And actually, there are solutions to this, starting with LSTM and nowadays transformers. But before that, you should understand the problem. I mean, LSTM is most probably the solution for any of these problems, but LSTM is handcraftedly designed to solve this problem. But before getting there, we should understand the problem. Okay, so vanishing gradients problem. By the way, another question would be, wouldn't they explode? Yes, depending on the initialization of the weights, depending on the update of the weights. The single value decomposition for this matrix can go over 1, which may explode it as S becomes large. This may be the case. For some cases, this could be. However, we never initialize them larger than 1. We always initialize them smaller than, in practice, smaller than 1. And on the other part, we usually use sigmoid or 10H functions that are bounded, because we need bounded functions for some different reasons. So depending on the generally used activation functions and the nature of the initialization we use, we hardly come up with exploding gradients. We usually come across vanishing gradient problem. Okay, as more layers are added to the neural network, the gradients of the loss function approaches to 0. This was a fact that was recently studied in convolutional neural networks as well. So that's why this paragraph is generalized, not for recurrent neural networks only. As the depth grows, it is difficult to train them because gradients vanish. Okay, this was something that we already know from deep CNNs. I'm sure you've already gone over it. And during the solution for CNNs, people have come up with different solutions. For example, VGG, we had AlexNet, then we had VGG, and with VGG, another group, Google, had the exception net. And in exception net, to make it work, because the gradients were vanishing as the depths get larger, if you remember the structure of the exception net, you don't have to, at some part of the network, in the mid parts of the network, there was another loss being fed to the network, just like feeding a bit more blood and gradient to the network so that it gets trained. People had some clumsy solutions, tried some clumsy solutions to it. So this was a problem. Gradients vanishing after the depth is getting larger. And in the context of RNNs, depth getting larger is sequence getting longer. Okay, truncated backpropagation through time could solve some problems, but it is a handcrafted design and it has its own problems, just like we discussed. The model must learn long-term dependencies. What if the model should learn long-term dependencies? Who's going to solve that? Apparently not truncated backpropagation through time. So we need recurrent neural networks that are capable of learning long-term dependencies. So I'm going to first remind you how this problem was solved in CNNs, because that solution is actually a solution which is inherited from the recurrent neural network world, if you don't know it already. I'm going to get there. This, in CNNs, one of the famous solution to depth problem was the residual networks by Kai-Ming He in 2015. By the end of 2014, in Oxford, VGG, or in Canada, Montreal, Hinton's group, AlexNet, or in Google, Exception, I mean, the deep learning researchers of the world have realized that we can't get deeper. And as the network gets deeper, we have worse results. The gradient is dead. And in 2015, Kai-Ming He, a young guy from China Microsoft Research, came up with this idea, this residual neural network. The idea was very simple. Instead of using a convolution block, this guy proposed the residual block, in which we have two convolutional blocks. Weight layer is the convolutional block. So it's like a double convolution network. But to the next activation function, which is usually a ReLU, rectified linear unit in convolutional networks, a skip connection, an identity connection, was summed up to the output. The idea was simple. When you look at it from the forward run, if the weights are zero, I mean, if the activation is dead, this guy will follow here. So the representation won't lose anything if these weights didn't mean anything. So that layer would be a waste of layer, but it wouldn't be killing the activations. If you think of the backward pass, if the gradients die here, according to the rules of how gradient is backpropagated in a network, computational graph, this high wave path will allow the gradient to flow from here. So it will never die. This design led Kai-Ming He to create deep networks of hundreds of layers. And ResNet, you know what ResNets are. So this idea actually in 2015 was an idea which was inherited from LSTMs, guys. LSTMs is 96. Kai-Ming He checked LSTMs. We had the vanishing gradients and deepness problem in recurrent neural networks. And they solved it with LSTMs. You don't know this, we are going to get there. So I should apply it to CNNs now. But the strange thing is, in today's deep learning courses, you first learn CNN and ResNet. Then in a sequence model, you usually learn RNNs and LSTMs. So the chronological order you learn and the chronological order in their history are the opposite. How to solve it in RNNs? Truncation was a way, but definitely not the correct way to do it. There's an ultimate solution to this. Just like Kai-Ming He did for CNNs, we can do this kind of a handcrafted design to RNNs and solve it. And actually it is solved. It is the famous LSTM, which we will be talking about next week, okay? But before that, I've mentioned a lot about RNNs, how they are powerful, how they are not powerful, what is their problem. I'm going to be doing a very simple live code to show you why they don't work. It's a very simple example. It both shows the beauty of RNNs because they are capable of many things. But when you feed after a threshold, I mean, when you push them a bit more, you see their weakness and why they can't work. So I think in deep learning, the best way to understand the concept is to first understand it theoretically, then you must try it practically to see the results with different examples. Okay, before getting to that, I'm going to talk about an example here. So people did not give up to this problem. In Hinton, again, and some guys, they tried to come up with a way. I mean, they asked the question to themselves, okay, recurrent neural network is very difficult to train, definitely. Geoffrey Hinton has famous speeches on this. Could there be a way to initialize recurrent neural networks such that this problem is solved? So following this scientific question, they had a nice paper. So before the live code, I'd like to mention about this nice paper. The idea in this study is called the identity RNN. An identity recurrent neural network, IRNN, is a vanilla recurrent neural network in which recurrent weight matrices are initialized with the identity matrix. So it is like, initially there is no correlation between the states of the network. Strange idea. The biases are initialized to 0, and the hidden units are rectified linear units. So it is like a node of a convolutional network which has a recurrent connection, and initially the hidden states are uncorrelated. I think this is a very nice thought experiment. And the paper, it come up with the results that an identity recurrent can be trained more easily using gradient descent as opposed to vanilla RNN. There is not an identity RNN because when we are initializing vanilla RNNs, we don't initialize them the diagonal matrix, hidden states having no correlation or 0 biases. And it does not suffer much from vanishing gradient problem. So yes, mathematically, there could be ways to overcome this. But today we know that it is not the solution to solve this. Okay, what to do until next week? We are going to do the live code now. It's going to take a while, don't worry, we're not finishing, but let me finish these slides. Check the suggested reading, interesting stuff. I'm sure you already have your environment, you're proficient in deep learning. If you have never done a sequence modeling code, check the live code that I'm going to provide because I have it on OptiClass. You can find better codes, but this is a very simple one, and any problem could be applied to it. But still, it will be. I mean, it's a toy example. It won't satisfy your needs for your project, but you can check. But if you have done some sequence modeling in your lives before, because there are people like that. For example, Esat is a PhD student who is already working on this kind of stuff in his work and his PhD thesis. So if you're already working on some stuff, this live code will be trivial to you. But if you haven't, it's a good place to start. And if you haven't done it already, start thinking on a project idea. Okay, next week we are doing the LSTM. We are doing the handcraft. We are going over the handcrafted design, which will lead us to a solid tool of sequence modeling, which is being widely used today. So history is finished with this week, guys. Starting with next week's subject, the tools will be the tools that we use and experience in our everyday world, okay? Okay, additional reading and stuff. I get to my live code. Can everybody see the live code? I guess so. Let me just, can I make it larger? I don't have a proper mouse here, so I have a mouse here. Sorry about that. Okay, let me get the mouse. Sorry, I'm going to make you wait for a minute. I'm borrowing the mouse of the desktop in the classroom. Okay, so I can make it larger, right? Please get larger. Okay, let's get it smaller. Okay, so you can see it better now. This is vanilla RNN Pi, nothing else, the simplest code you can find. In this code, we are going to be teaching a very simple network, a sequence of characters. And we'll be doing no embedding. What is an embedding? Most of you don't know what is an embedding maybe, or many of you will know, I don't know. We are going to be talking about embedding today. Embedding is like the features for a natural language process. So I'm doing no feature extraction. if, this could have been, this is an NLP example, but this could have been a signal processing example, like image processing or sound. In those cases, you usually have some sort of features extracted and fed to RNN. And they are called CNN plus RNN architectures, which we'll be covering in the following weeks. But this is a very simple example. I'm feeding characters to a very simple RNN. I'm going to go over the code. But quickly, to make you understand what the problem is all about, let me show you my model. Where is my model? Yeah, this is the model. It is, sorry, where is my, yes, and where's my, yes, it's, I cannot see. It is the RNN as a fully connected layer. That very simple core RNN plus output layer we have seen previous week. Nothing else. I'm going to be feeding a sequence of characters to it. And I'm going to show you the associative memory ability of RNNs. And I'm going to show you the limits of it. So this is my training set, line 18. Some sequences, guys, sorry, let me make it bigger. So some sequences. How are you? Good, I'm fine. Have a nice day. 3 sequences. I'm going to teach this guy these sequences. This will be a very simple network. And I'm going to be fixing the back propagation length. So it is maybe the most simple RNN example you can find. Because as you can see, these sequences have different lengths. I'm going to make them same length by adding spaces. So these are the texts. Here I convert these texts to characters, these characters to integers, so that I'll be feeding numbers. Like it's a sort of like an embedding. Embedding is a feature extracted for an NLP training set. So I'm going to put them. So as you can see, actually I've already run it. So as you can see, it is here. E will be 0, space will be 1, A will be 2, R will be 3. And actually, I'm going to be using the corpus of characters that I only have in my training set. So I have, for example, in this training set, 17 different characters, including the space. That's why my little training set here goes from 0 to 16. Okay, so when I, in this line, when I printed character to it, I'll have this. This will be my embedding. So this is the first time I'm giving you the idea of an embedding. Actually, we are going to go over it in detail. But if you have taken Tuğba course, text analytics, you already know deep detail what embedding is. I'm going to be delving into it in an introductory level in this course, but if you have taken that course, you know what it is, or if you have been working on it. Now I'm going to make this problem very simple. I don't have to, because this is an example I borrowed from the internet. It is what it does. I'm going to check the maximum length of the string. The longest string has, it's going to say, for example, the longest. Can you see it? The longest string has 15 characters. The other sequences in my training set are shorter. I'm going to embed some spaces to it, so they all become the same. Why am I doing this? To make my training simple. Because I'm going to be backpropagating and truncating or longing the training, because I'm longing it for some sequences, to this fixed value. I'll be training them 15 times. So during my training, since my sequence will all be 15, the weights will be updated for each sample of the training set 15 times. Good. Then this is the part where I add the spaces, and they're all 15 length sequences. Then I put them in a list format. List, you're familiar with Python, I'm sure. List is the common format that we keep different types of variables. It's common data type in Python. I'm putting them in lists. So there are some lists. I have a list of 3 elements because that's my training set. And I train them. Okay. Very simple. So, so this is my dictionary size. Why this is my dictionary size? Because while you're training RNNs, there are some parameters you should feed to the RNN. So what is the length of the sequence, the vector? The vector is a single character. I represent that single character with a value. So what is the range of that value? What is the dimension of that value, for example? Actually, in this case, we are feeding it with hot1 vectors. Hot1 vectors is when you represent something like this. It's an hot1. So for example, there's a chat. Okay. There's a question, I'm sorry. Oh yeah, okay. I stopped the live code. I'm going to answer the question. Hocam, I want to ask that torch inherent LSTM structure fixing the length for LSTM is the speeding up the LSTM for torch implementation, or another question maybe, does padding with space worsen to improve performance compared to given by 1Y padding? Definitely padding with space worsens the performance. This is a toy example. To make things simpler and to make everything simple, we do this. About the LSTM question, I couldn't quite understand the question. We are not covering the LSTM right now. So you're asking a question about LSTM. Is the question about this week or is the general question? LSTM structure.
I just want to ask that, I mean, torch, for it can be also RNN. I mean, they are fixing the batch. So is this, I mean, this is for speeding up or just for a proper coding style?
No, it's for speeding up because you know that they can only get one by one pieces. I mean, when they're taking, it's difficult for them to work on a varying length of data because although it's a sequence, this guy is doing them just in batches. That's why it's doing it. But still, I mean, this is not padding zeros. I mean, it is not updating the weights for it. It's just trying to, as far as I know, make its structure compatible with the computation. Did I get your question correct?
Yeah, Hocam, thank you.
Okay. That's what I know about it. Let's say it's an issue. Okay, so about the second part of your question, does adding space worsens the performance? That's not the way to do it. But this is a toy example. I mean, this is the first sequence modeling example we have, and I think it should be a toy example. If there was a lab for it, this would be the first example we have got, because that's the thing we have seen, core plus the output RNN. If this is the first time you're seeing an RNN, that's the perfect example. If you have been working on sequence models, yes, this is a 3D example. So where I was, one hot encode. So this guy is doing a one hot encode. One hot means, encode means, in NLP, one hot encode means. So as you can see, sorry, let me change my color. E is 0. For example, as you can see here, H is 16. So E will be represented in a 16 by 1 vector where this is 1, these are zeros. And for example, H, this is H, I'm sorry, H will be represented 1. This is one hot representation. So I'm embedding the characters to representation where they are all orthogonal to each other. Because if you multiply this matrix with this matrix, the orthogonal distance is the same in this character to another character, for example. These are the subjects of embedding. I mean, they are not necessarily important for us right now, but they will be important for us in future. Okay, so I convert them to one hot encoding, and I feed them to my neural network. Okay, so the first layer is the RNN. So the RNN will be getting an input of 17 length vector. So when I'm creating the RNN, I am providing this dictionary size as a parameter to RNN. Another parameter will be the number of hidden states. I just designate the number of hidden states somewhere here. I'm going to find it out. Okay, so these are the input sequences. You embed them to a one hot representation, and you just select if there is GPU or whatever. These are trivial. This is the model. And when you're creating the model, you provide the input size, which is the dictionary size for us, and hidden layer size, and number of layers, if there will be multiple layers. There won't be, this is a simple RNN. In the RNN implementation of Torch, you can create multiple layers with different weights. You don't have to do it, you can do it in encoder-decoder design, which we are going to see in the following weeks. This could be a case. We are not going to do it. It will be one. And there will be the FCC layer. And if you know Torch, when you define the forward connections like this, so you provide the forward connections, the output will be fed to the FC. When you define the forward connections, PyTorch automatically creates the backward connections because these are all Torch functions. Okay, so you create a graph using the forward connection. The elements of the graph are already inherited from different PyTorch libraries. In that case, PyTorch can automatically create the backward run for training. That's what PyTorch does. Should you already know this? Okay, number of epochs, learning rates, I decide and I define. Hidden dimensions, I decide here is 12, as you can see. Dictionary size is the input size and the output size, because dictionary size is 17, that represents a one-hot vector. And I'll be feeding vectors and vectors. So it will be like this guy. How it's going to work? Let me show you. So this will be the RNN. So I'm going to be feeding a character, the first character. This will be the RNN cell. It's going to output me another character. Okay, for example, N. I'm going to feed it to as the next sequence. That's how I'm going to work. So I'm going to be feeding. So in this example, I'll provide one character and ask for the rest of the characters. So it is like, it is connected this way. I'm connecting the output of the RNN to the next one. That's how I'm going to train it. So these will be the outputs. So it is like, if I'm going to be training this with how are you, the input to H will be O, the input to O will be W, kind of. Input to W will be blank, because in how are you, that's the order of characters. That's the example I create here. I'm sure you got the idea, right? So that's how I'm going to be training the system. So I'm going to be training the system with these guys here. And in the end, to check my results, I'm going to provide one or more characters. I'm going to say, hey, and see the results. Create some results for me, I'm going to say. Since it is limited to 15, it's going to give me, I'm going to be 15, I'm going to be giving 15, but I can do it more. I can just say 10. I can run the trained system 10 times or 15 times, doesn't matter. Okay? But I'm going to do it with 15 because I will train it with fixed 16 length sequences. And if they are not 15 length sequences, because 15 length, if they are not 15 length, I'm adding padding zeros, not zeros, blanks to the end, remember? Okay, and this is the predict model. This is the sample model. And I'm going to train it, okay? It's a very clear code. Here's where I train it. I just train it for 100 number of epochs. So it's very simple. These are the character sequences here, line 18. An RNN with a 17 length hot vector input and some very low number of hidden dimensions, 12. Very simple. It's a very simple network. And I get the results. At the output layer, I have the hidden state 12 being lowered to a 17 vector, which is the hot vector. Okay, good. Let me run it. Let me run it. When I run it, and each time I run it, I'm going to train it from scratch because it's very fast. And I'm going to ask for H, and I'm going to tell it, run it 15 times, and let's see what it creates. Yes. When the input was H, the output was, hey, how are you? Let's get the training set. Yes, we have an example in training set starting with H. Okay, let's try the other one. Let's start with G. Will it follow the example in the training set? Okay, I think it will, because it has the ability to learn. So now we're testing this simple network's ability to learn. Good and fine, yes, very nice. In a couple of examples, I'm going to be getting out of these training set starts. Let me say there was an H here. When given H, it decided on H, E, hey. Let's say we have, not H only, HA, which is another start for the training set, right? Have a nice day, it says. Now let's change things. Let's say T. We don't have it. Have a nice day. Do we have it? Do I have T? Do I have T here? No. Because it should be in my list of words, characters. I don't have T. I'm going to say A. I have A. No such sequence starting with A was provided during training. It's a very funny example. It creates a slang word language. It's like a street language word. I say M-U-R-U kind of, or just say Y. It creates this. And given that, you don't find. Given these examples, it's a nice way of showing how fast RNNs can overfit to a training set. And simple words as well. With this very simple example, 12 hidden states and a limited number of characters. We don't have all the characters of English language, not all of them. Still, we have some fine results. It doesn't provide me with rubbish, as you can see. This shows the strength of RNNs. Let me just give you, you can try it at home. You can play this with them anytime. Say start with A. But let me show you, it's fun. I'm kind of. So it's trying to make up, with this very little capacity, trying to make up sentences which look like it makes sense. However, let's talk about the weaknesses of this guy. If you want to find the weaknesses of this guy, RNN, you should push it more. So what I'm going to be doing is, I'm going to be pushing it with a larger data set. As you can see, larger one. Hey, how are you? Good, I'm fine. Have a nice day. Hello, good morning, good afternoon, good evening. It's nice to meet you. It's a pleasure to meet you. I didn't change it much. I mean, looking at our level of understanding natural language, is not much a change, right? But it is for this simple model, guys. Let's train it. Okay, we had I. Let's give H again. H. Remember when in the previous model, which was trained using 3 samples, it directly gave one of the training sets. Will it do it now? Unfortunately not, guys. Although there are multiple samples in the training set starting with H. So let me just try to make it simple for it. I provide another sample, still not. I provide another sample, it's still not. Because during training, I have provided different sequences and different sequences. And they were training the same weights over and over again. And the capacity of this recurrent neural network was not enough to learn this many samples. So as you can see, depending on the capacity of the recurrent neural networks, you can easily make them learn things. However, they are very fragile for hyperparameters, for the training set, and the architecture of the network. Still, it's a very simple architecture. So I believe that as a toy example and as a starting example and as an initial example, this is a very nice example of showing the beauty, strength, and the weaknesses of vanilla recurrent neural networks. Any questions about the example? Okay then.